We're now going to look at the formal definition of a plane and look at some of its really simple geometric properties. And the simplest type of function where you have ordered pairs being associated with real numbers. So the simplest type of function of this form, right, is, so I'll write it like this: f of x, y is equal to, so if I just have, so if I have my variables present, like x and y, so I could have like a constant times x, and then a constant times y, and then add another constant right here. This is basically the simplest type of a function of two variables, right? And so it could be written like this, or we could explicitly say that z is equal to ax plus by plus c. And this type of function, right, defines a surface, so which defines a surface that is known as a plane. Right? So of all all the operations that we can do with our two independent variables x and y, if we simply multiply each variable by a constant and then add another constant, that is how we get a plane, right? But that really doesn't tell us a lot, So let's look more closely at this idea of a plane. So at the very least, since we don't have any x squareds or square roots or sine functions, since we don't have anything non-linear on this side, we would expect that if we were to plot a surface of this form, right? And I'm not going to put the x, y, z axes, but here we have a plot of this. We would expect it to be something flat, something linear, right? So this is a flat surface. This is something linear, right? Because it's not curved, it's not bendy, right? And of course, so then you would have lots of points on this surface. Like a perfect example of a surface is like the cover of a book. It's flat. So how do we describe this mathematically? How do we derive, how do we go from this flat concept to an equation that looks like this, right? Well, let's see. Now, what's interesting is if I take a vector that is normal or orthogonal or perpendicular to this flat surface, then it would look, kind of like that. So if I take a vector like this, and of those three synonyms that I just said, we're going to stick with the word normal. So I'm going to use n here. And it is a vector, right? It's a vector that has an initial point somewhere in the plane, right? And then it obviously has some terminal point here. And I'm just going to say, let's say we have the component form of this, A, B, C. And in fact, n is called the normal vector. So n is called, well, actually, I should say a normal vector of the plane. The reason why we say that it's a normal vector and not the normal vector is because once you have one normal vector, you technically have infinitely many normal vectors, because any scalar multiple, any non-zero scalar multiple of this green vector will still be normal or orthogonal to the plane. So even if I shrink it, so if it's just that instead, even if I make it negative, So I'll draw these dotted. Even if I go this way, so it's 90 degrees there, it's 90 degrees there, right? So I'll just say that this any non-zero scalar multiple of n is also a normal vector, right? We don't really care how long it is, right? We don't care about its magnitude. We only care about its direction, right? So, for instance, so a vector that goes like over here would not be a normal vector because it wouldn't form 90 degrees. Okay. So the initial point of this normal vector, let's give it some coordinates. So, in fact, let me do this. So this is going to be the point P0, right? At some point, it's going to be in the plane because this is a vector that initiates in the plane. So it's x0, y0, z0. And then suppose I pick any other arbitrary point in the plane. So again, going back to my analogy of the cover of your book, pick one fixed point anywhere on the surface of your book, and that's where we're going to draw the vector that is perpendicular to the cover of your book. And then somewhere else, pretend that there is a point that, it can move freely. So it could be anywhere. So I'm gonna label that one P. And since it's not fixed, I'm not going to put subscripts there. Usually, when you put subscripts, it usually means something is fixed. Even if you don't know exactly what it is, it means that, okay, this one stays put and this one is allowed to roam free. Okay. The interesting thing, though, is if I form the vector from my fixed P0, and instead of going up or instead of moving in a direction that is perpendicular to the plane, what if I moved in a direction that, in other words, just draw a line, like I would draw the vector on the cover of your book going from P0 to P1, right? So the normal vector is n, and then any vector, so the vector P0 to P, and let's write down what the components of that vector would be. Since it's starting at P0 and going to P, this other point here, if we use our head minus tail, it's going to be x minus x0, y minus y0, and z minus z0, right? So we now have two vectors. We have our normal vector, and then we have this arbitrary vector that's in the plane, right? And just imagine if there was a slider where you could sort of move it about, right? But the thing is, that vector that's in the plane consists of many points, infinitely many points, also in the plane. So for instance, if I were to slide my normal vector now, where I don't change the direction, but I change the initial point, and let's say I moved it along the red line, it's kind of sliding it this way. Regardless of where I put the initial point of my normal vector of n, as long as I don't change the direction, it will still be at 90 degrees. So what that means is my green vector n is always going to be orthogonal to my red vector P0 to P, right? So since this vector P0 to P lies in the plane, right? So again, just imagine like you just draw a line on the surface of that that book. So since P0 to P lies in the plane, I can't spell today. So in the plane, what is always true? That regardless of x0, y0, z0, this vector is always going to be orthogonal to this vector, right? Well, what do we know about vectors that are orthogonal? Their dot products are always 0. So that means, so now I start to get to some equations, which we love. So what this means is if I take the vector P0 to P and I do the dot product, so this is my nice big dot product with the vector n, then that has to be equal to 0, right? And this is kind of, well, it's getting there, but this is essentially the vector equation that defines a plane. If you have an arbitrary, and when I say arbitrary, if you have a general vector in the plane, and then you have a fixed vector that is orthogonal to the plane, then the dot product of those two vectors must be equal to 0. Well, let's actually write down, because we have the components of both vectors, let's actually write down this expression and see what the dot product actually gives. So here are the components of my vector in the plane, right? And all I need is, I have my variables x, y, z, and then I have the coordinates of a fixed point. Do the dot product of that vector with the vector that I just said, whatever the components of the normal vector are, your a, b, c. And what defines the plane is that we're saying that this dot product is equal to 0. Well, we know how to compute a dot product. Take the first component of my vector in the plane and multiply it by the first component of the normal vector. So I'll just do a times that quantity. So therefore, we have a times the quantity x minus x0 plus b times the quantity y minus y0 plus c times the quantity z minus z0, and then that has to be equal to 0. And this is a very important equation. This is it's called the point normal equation of a plane, right? So let's write that down. So this is the point normal equation of a plane, right? Okay, so that's good. But now, if for instance we said, what if I wanted, so remember where we started? We basically said that, and I'll kind of write this in quotes, that the equation of a surface, because if we want it in this particular form where we want to have our z, which we're going to assume is our dependent variable, we would want it to be kind of in that form, where you have a constant times x plus a constant times y plus another constant. So what we could do, actually, is we could take this equation and convert it to this equation where we actually isolate the z. So if I were to solve this for z, the first thing I would do, I would move these two terms over. So let's say solving for z, we'll have c times the quantity z minus z0 is equal to negative ax minus ax0. Well, that will be plus now, because when I move this term over, this coefficient becomes negative, but after I distribute it, those two negatives will make it a plus ax0. Same thing for the term with the y, so I'll have minus by, and then plus by0, right? And then since I'm trying to isolate the z, I would divide through by c, and once I do that, I'm assuming that c is not 0. So if c is not 0, then it will have z minus z0 is equal to all of this divided by c. And what I'm going to do is I'm going to say negative a over c x minus b over c y, and then all of these. Now these are just constants, right? Because the x0 and the y0 is a fixed point, but my regular x, regular y, those are true variables. These are my coordinate variables. So then I'll have plus ax0 plus by0, and then add z0 to both sides, and then we get this. So negative a over cx minus b over cy, and then I basically have plus ax0 plus by0 plus z0. So why am I going through the trouble of doing this? Well, it basically shows you that, yeah, we've now expressed the point normal equation of the plane in this alternative form. Because it's like what I have here as my coefficient of x is some constant, which I could say that it's this. And what I have here as the coefficient of y, that's, again, that. And then all of this is just a constant, right? Because the a and the b are the component, or the first two components in my normal vector. And then the x0, y0, 0, that's just, again, a fixed point. So that would be like this constant here. So this type of equation, assuming that we're treating z as our as our dependent variable, and then x and y as our independent variables, this type of an equation is the explicit form. So it's your explicit form, right? And then this would be like your implicit form. And again, and this is a notion that we're going to come back to, that surfaces, not always, but in many instances, a single surface could be defined, let's say here, z as a function of x and y, and that would be the explicit form, or it could simply be an implicit form where you basically have all your variables, let's say, on one side of the equation, and then you have a constant on this side, right? But what really what makes this a plane is the fact that the expression that we have here is linear in terms that all of your variables, the most you're doing is either multiplying by a constant, or in this case, like subtracting a constant. So you're not like, you don't have an x squared, or you don't have an ln of x or anything like that. Those terms would make the surface non-linear, and it would not be a plane. All right. Okay, so let's do a couple examples of planes. So let's see what we got here. So what is the equation of the plane passing through passing through 1, 1, negative 1, 2, 3, 4, and let's say 0, 0, negative 3. All right. Okay, so in this question, we are given 3 points, right? And we are asked to find the equation that defines that that plane, right? And well, how would we do this? So again, I'm not gonna, label things trying to be so precise, but let's just call this A, this B, this C. So we have these 3 points. So I have them like this. All right. And so these are 3 points, and we want the plane that passes through these 3 points. Well, in our definition with the point normal, we only needed 1 point, but we needed the a normal vector. So in order to find a normal vector, I would need to find, so let's say the plane. So let me label these A, B, C. Let's say that the plane is like that, like let's say this is just a portion of the plane, right? So this is a portion of it, but it extends indefinitely that way, that way, that way. So this is like that flat surface, right? But again, I'm just drawing just a small portion of it. What I want to do is to find, now remember that the whole idea with the normal vector is you can have it with an initial point at any point in the plane. I could start it here, I could start it here or here. The whole idea is it's going to be orthogonal to the entire surface, no matter where I start to draw the normal vector. So let's say, just for convenience, let's say I put the normal vector right there, right? That's the normal vector. Again, I could have put it at B, C, or at some other point in that shaded region. I just have to make sure that it's pointing in that same direction. Well, how do I find my N? That's kind of what I need to do. Well, the interesting thing is this is a really cool application of the cross product, because I could define two vectors in the plane. I could define the vector that goes from A to B and the vector that goes from A to C. And now, since I have two vectors and I want to find a third vector that is orthogonal to AB and AC, I could say that N is actually equal to the cross product of the vector AB and AC, right? And then that will give me my N, right? So this question has a few key steps, right? So let's go through and first find the components of the vectors A, B, and AC, right? So looking at the points that are given, the vector AB has components 2. Let me see. Oh, that yeah, that's a 1. So 2 minus 1, so that's 1. And then 3 minus 1, that's 2. And then 4 minus -1, that's 5. And then AC is the vector 0 minus 1, so that's -1. 0 minus 1, another -1. And then -3 minus -1, so that's -2. So we found these two vectors in red. Now let's use the cross product to get the vector in blue. So the normal vector, or a normal vector, remember you can use any scalar multiple of the normal vector that you want. That looks more like an H than an N. So we're going to use our cross product. So it's AB crossed AC. It doesn't matter the order in which we do the cross product. If let's say this is the direction that would give me the normal vector going this way. Remember, when you switch the order of a cross product, it changes the sign of the vector. So if I did it AC crossed AB, I would get this vector here, which would still work. It's just, again, a different normal vector, right? So you can't really mess this one up. It's just a matter of making sure that you first find two vectors in the plane and then do the cross product. So let's do our I, J, K. And so fill out the second row with 1, 2, 5. Third row with -1, -1, -2. And then we're going to use, again, our cofactor expansion with the first row. So let me write down the 2 by 2 determinants that we need. So blocking out the first column in the first row leaves me with this submatrix, that's times I, and then minus, let's block out the middle column in the first row. We're left with 1, 5, -1, -2 times j, and then plus, block out the third column in the first row. That leaves the 1, 2, -1, -1, and then that's times k. So the components of the normal vector, or a normal vector, is -4 minus -5, comma, put a negative out there. We have -2, again, minus -5, comma, and then -1 minus -2. And there we are. So here are the components of a normal vector. That's 1, -3, and 1, right? So 1, let's make sure that's right, because that's 3 and the negative. Yep. So here's our normal vector of our plane. And just note, any scalar multiple of this would work. I mean, there's no real need to change this, especially when you look at the coefficients are expressed in terms of, there are no common factors here. But if, for instance, you wanted to, let's say, double all of these components, then you'd have 2, -6, 2, right? If you wanted to take a half of these components, you could have a half, -3 halves, -1 half. If you wanted to multiply by 100, you could have 100, -300, 100. These are all valid normal vectors for this plane. It's just a matter of finding one that's convenient, but really there is no need to modify it. So the point normal equation of the plane is, so now we have a choice, right? I know that, so I'm going to use the 1, -3, 1 as my A, B, C. But which point do I use? Which point do I use? And the thing, like I said, it doesn't matter which point, right? As long as I've correctly computed a normal vector using the appropriate vectors in the plane, I can choose either A, B, or C. Again, let's just say using A. So it is, so I'll just, if we use A, 1, 1, -1, then this is now my x0, y0, z0. So it is 1 times the quantity x minus 1, and then plus -3 times the quantity y minus 1, plus 1 times the quantity z minus -1. So there I'm using that equation, but again, it says an equation, so until I put the equal 0, it's not the equation of a plane. It's just some expression. It's a linear expression, but it's not an equation of the plane until I do this. And then, we could, let's say we wanted to put this in the explicit form. Now, the question didn't specifically say what form, so this would be a completely acceptable answer. So would this. So if we distribute the -3, distribute the 1, so plus c plus 1, that would be completely valid. What I'm about to write down is kind of another standard way of writing the equation of a plane, where you keep all the variables that are present on the left-hand side. So you have the x minus 3y plus z, and then you move all the constants to the other side. So let's figure out what the constant is. Well, we're left with a constant of a plus 3 on the left-hand side. If I move it to the right, then it becomes a minus 3. So this is another typical way that the equation of the plane can be given. Now, if I wanted to write it as a function, an explicit function of x and y, then z would be equal to negative x plus 3y minus 3. So all of these are completely valid equations of the plane. All right, there you go. So just with the idea of vectors and orthogonal vectors, we can come up with a very useful equation for the equation of a plane. See you in the next video.